In this video, we discuss the general solution of homogeneous linear ODEs, and specifically, we build up to that by talking about 5 facts about linear homogeneous ODEs. So here's just a reminder of what a linear homogeneous nth order ODE looks like. This is nth order because the highest order derivative here is the nth derivative of y with respect to x. This is linear because the derivatives, you've got the nth derivative right here, the n minus 1th derivative here, the first derivative, the 0th derivative. All of those are raised to the first power, or they don't appear in the equation at all if that coefficient function happens to be 0. The coefficients out front, a sub n of x, a sub n minus 1 of x, a sub 1 of x, a sub 0 of x, all of those depend only on that independent variable x, and the function on the right-hand side depends on the independent variable x. So if a differential equation can be written like this, where all the y's are on this side, and a function of the independent variable is on this side, and when you put all of the dependent variable terms on this side, if those dependent variable terms that are involving the derivatives of the dependent variable or the dependent variable or the function itself, put all of those on this side, if they all appear at most to the first power, the coefficient functions at most depend on the independent variable, and you don't have any composite functions involving y or y's derivatives or the dependent variable and the dependent variable's derivatives, this is called a linear nth order differential equation. Now, if this right-hand side is 0, we say that the differential equation is homogeneous. If it's not 0 for any value of x, so let's just say it was x squared or sine of x, if there's actually a function there other than 0, we call that non-homogeneous. So what we're about to talk about only applies to homogeneous equations, so that's where the right-hand side is 0. Okay, here's the first fact. This nth order differential equation always possesses the trivial solution. So y equals 0. Oh, I wrote x. Y of x is equal to 0 for all values of x. I think it's obvious why that's true. If this is a 0 on the right-hand side, if I take 0 and I plug it in here, I've got something times 0, which is 0. The derivative of 0 is 0, so that guy is gone. This n minus 1th derivative of 0 is 0, so that guy's gone. All the terms are going to be gone because all those derivatives and the function itself are all 0. And if I plug those in on this side, I get 0, and that's going to be equal to the 0 on the right-hand side. So this always possesses the trivial solution. But typically, if we're looking for the general solution of the differential equation, that trivial solution is not the solution that we're looking for. Here's another fact. If y is a solution to this linear homogeneous ordinary differential equation, then a constant times y is also a solution. And I think that makes sense. If you think about it, let's assume, we can prove that pretty easily. Let's assume that y is a solution. And then substitute c times y into this differential equation. So let's let y star equal c times y. Then if I substitute y star into the differential equation, I've got n sub n of x times the nth derivative of c times, or times the nth derivative of y star, which is just c times the nth derivative of y with respect to x. Because the derivative of a constant times a function is just the constant times the derivative of that function. And then I've got a sub n minus 1 of x, that coefficient function again, times the n minus 1th derivative of this. Well, I would just factor the constant out and multiply by the n minus 1th derivative of y. And you just keep going. Got a sub 1 of x here, And then the first derivative of this guy is just a constant times the first derivative of that function that you already know satisfies the equation. And then you've got a sub 0 of x times y, and we're substituting in y star. So that's c times y. So this is what we get when we substitute y star into the left-hand side of that differential equation. Now notice that all of these have a c in common. I've got a c here and here and here and here. I can factor out a c from everything. So we're left with this. You've got c times the nth coefficient function times the nth derivative of y with respect to x, plus the n minus 1th coefficient function times the n minus 1th derivative of y with respect to x, and so on. We're going to eventually have a sub 1 of x times the first derivative plus a sub 0 of x times y. Well, that's just the left-hand side of this differential equation. And if we're assuming that y is a solution, if you plug in y to the left-hand side, you get 0. That's what it means to be a solution. So you end up with c times all of this, which is 0 because y is a solution. So you've got c times 0, which is 0, which is the right-hand side. So that means that y star, which equals c times y, is also a solution. Now I know that that's a little abstract. We didn't do it for a particular differential equation. We just did it in general because I was trying to prove that this is true in general. If y is a solution, then c times y is a solution to this, this nth order linear ODE, and it's homogeneous. When we're looking at the homogeneous case here, everything in this video applies only to homogeneous ODEs. Things change a bit if the right-hand side's not 0. Okay, so I just showed you that that was true in general. Let me give you a specific example just to make it a little bit more concrete. So let's say you've got this differential equation, 3t squared times y double prime minus 2t times y prime minus 2y equals 0. Let's say we want to verify, sorry about that, verify that y equals t squared is a solution. And then we want to show that y star equals a constant times t squared is also a solution. In order to verify that y equals t squared is a solution of this, we've got to take the derivative twice and then substitute into the differential equation. So if we have y equals t squared, y prime is just 2t, and y double prime is the derivative of 2t, which is a 2. And we substitute those into this equation. So you've got 3t squared times y double prime minus 2t times y prime minus 2 times y. We're substituting into the left-hand side. Y double prime was 2. This is supposed to be y prime. We got a 2t there. This is supposed to be y, which we assume to be t squared. If we evaluate this, we get 6t squared minus 4t squared minus 2t squared, and that minus that is 0. So the left-hand side simplifies to 0, which is equal to the right-hand side. So when y equals t squared, the left-hand side equals the right-hand side. Therefore, y equals t squared is a solution to the differential equation. So we just compute the derivatives, you substitute into the differential equation. Well, actually substitute into the left-hand side. and then show that the left-hand side equals the right-hand side. Okay, now we want to show that c times t squared also works. So if you've got y star equals c times t squared, y star prime is c times the derivative of t squared, which is 2t, and y star double prime is the derivative of this constant times t, which is that constant. If you substitute into the left-hand side of the differential equation, we had 3t squared times y double prime minus 2t times y prime minus 2 times y. Y double prime is 2c. Y prime is 2c times t, and y was equal to c times t squared. And so we get this 6c t squared minus 4c t squared minus 2c t squared. And if you want, you could factor out that c, and you're left with this. That's exactly what we had over here. We end up with c times this, and that's all equals to 0 because y equals t squared was a solution of the equation. Or you can just evaluate that and you see that 6t squared minus 4t squared minus 2t squared is going to give you a 0, which equals 0. And that's equal to the right-hand side. So y equals c times t squared is a solution to the differential equation as well. And again, you're substituting into, keep doing that, not the differential equation. You're substituting into the left-hand side, and you want to show that the left-hand side equals the right-hand side. If you can show that, then you have verified that your function is a solution of the differential equation. Now, I wanted to show you with a concrete example what happens here, and I wanted to show you by factoring out that c, because that's why this works in general. When I take the nth derivative of this, I just get c times the nth derivative of that first solution, and c times the n minus 1th derivative of the second one, and so on. And so when I take out that factor of c from everything, I just get the left-hand side of the differential equation, which I know is 0 at the solution y, because that's what it means for y to be a solution. When I plug in y over here, I get 0 because it's a solution to the homogeneous equation. So that's how it works in general. This is a concrete example, but I wanted you to see that when you actually do it with a function, you factor out that c, you get exactly the same thing over here that you got over here when you were verifying this solution. Okay, so we've got 2 facts so far. The first is that the DE always has the trivial solution, y equals 0. And the second fact is that if y is a solution, then a constant times y is also a solution. Now here's another one that might be surprising. Third fact. If y1 and y2 are solutions, then a constant times y1 plus a constant times y2 is also a solution. In order to prove this, we will assume that y1 and y2 are solutions. So that means if you substitute those into the left-hand side, you're going to get 0 on the right-hand side because the right-hand side is always 0 with a homogeneous differential equation. And then we're going to let y star equal c1y1 plus c2y2. Well, if I take the derivative of y star, I get C1 times Y1 prime plus C2 times Y2 prime, because that's how we take derivatives. If there's a constant, you just pull the constant down and take the derivative of the function. And then you add over here, you pull that constant down and you multiply by the derivative of the function. And you just keep doing this. And you're going to keep going. And eventually you're going to have the nth derivative right here. And I'm just using this prime notation rather than Leibniz notation to save a little bit of time. But this is because of what we learned in Calc 1. If you have the derivative of a constant times a function plus a constant times a different function, you just do this. So if we're letting y equal this, and these are all the derivatives, and then we substitute into the left-hand side of that differential equation, we've got a sub n of x times the nth derivative of y star. And I don't know why I changed it from a superscript to a subscript, but you get the idea. So we substitute that in right here. Don't let the change in notation get to you. It's exactly the same thing as that notation that we were using before. I'm just using prime notation rather than Leibniz notation. Then you're going to have the n minus 1th derivative times the n minus 1th derivative of y star. So that's going to be c1 y1 raised, or not raised to the n minus 1, but you're taking the n minus 1th derivative of y1. And then you're adding a constant times y2's n minus 1th derivative, and so on. And you're going to keep going until eventually you've got a sub 1 of x times the first derivative of y prime. So you have c1 y1 prime plus c2 y2 prime plus a sub 0 of x times y, the assumption that you're making for y, in this case is y star. So we've got c1 y1 here plus c2 y2. So we substituted into this left-hand side of the differential equation. And my goal is, remember what we're trying to prove, that if y1 and y2 are solutions, then this is also a solution. So my goal is to show that if I substitute this in and I assume that y1 and y2 are solutions, I still get 0. So this is a solution too. In order to do that, we just have to reorganize this a little bit. I'm going to focus on the C1 terms. I've got this one times this one with a C1, and then this one times this one with a C1. I've got this one times this one with a C1, and this one times this one with a C1. And so if we reorganize this and we factor out that C sub 1, we have C sub 1 times the nth derivative, or excuse me, the nth coefficient function times the nth derivative of y1 with respect to x, plus the n minus 1th function there, times the n minus 1th coefficient function times y1, y1's n minus 1th derivative. And you keep going, then you've got a sub 1 times y1 prime plus a sub 0 of x times y1. And that's just all of those that had a C1 in them. And then I want to group all of those that do not have a C1 in them. Let's group all of those that have a C2 in them. So you have to distribute, right? Because this is a binomial. So you've got this times this, and then over here you're going to have this times that, and this times that, and this times that, and so on. I want to factor out the C2 from the C2 terms, so I'm focusing here, and here, and here, and here now. I know this is a little bit of a mess, sorry. But I'm factoring out the C2, so I've got C2 times a sub n of x times the nth derivative of y2 plus a sub n minus 1 of x, that's just a coefficient function, times the n minus 1th derivative of y2. I don't know if I just said that wrong over here. This is the nth derivative of y2. That's the n minus 1th derivative of y2. And you keep going. You're going to have a sub 1 times that constant times y2 prime plus a sub 0 times that constant times y2. And since y1 is a solution, excuse me, it satisfies that differential equation. This is just the left-hand side of the differential equation. Since we're talking about a homogeneous differential equation, when we plug in that solution, we get 0. So this must be 0, and this must be 0, because y2 is also a solution. So I've got C1 times 0 plus C2 times 0, which is 0. And that is equal to the right-hand side. Therefore, y star equals C1 y1 plus C2 y2 is a solution. It all stems from this idea that if you have a linear combination of functions, this is how it would look in Calc 1. A times f of x plus b times g of x, where a and b are just real numbers. You'd bring the constant down and then you'd multiply by the derivative of f. And then you'd bring the constant down and you'd multiply by the derivative of g. This is a combination of the constant multiple rule and the sum rule that says the derivative of the sum is the sum of the derivatives. That's what we're doing here. If our differential equation is linear, so that means if y and y's derivatives are all raised at most to the first or they don't appear at all, and the coefficient functions depend only on the independent variable, and the function on the right-hand side depends only on the independent variable, then this will always happen. You're going to have C1 times 0 plus C2 times 0, which is 0. Okay. So if y1 and y2 are solutions, then a constant times y1 plus a constant times y2 is a solution. I'm not going to do another concrete example this time, but I will just state a concrete example. I'm not going to prove it this time, but I'll just state it for you. We were looking at this differential equation before. We said 3t squared times y double prime minus 2t times y prime minus 2 times y equals 0 has one solution of t squared. And in the last example, we proved that since y1 equals t squared is a solution, that implied that y equals c times t squared was also a solution. So this is a family of solutions of that differential equation. But there's actually another solution out there to this differential equation that doesn't belong to this family. It turns out that y1 equals t to the negative 1/3, or y2, excuse me, I'll call it y2. y2 equals t to the negative 1/3 also works. If you're not sure, you should take the second derivative, plug it in, and show that you get 0. Well, if y2 is a solution, or if y2 equals t to the negative 1/3 is a solution, then from our second fact, y equals c times t to the negative 1/3 will also work. So if I want a solution that takes both of these solutions into account, it turns out that you can use this solution. Y of t equals c1 times t squared plus c2 times t to the negative 1/3 is a family of solutions of this differential equation. If you take the first and second derivative of this and you plug it in and you simplify, you're going to get 0. Okay, so we had 3 facts so far. We said a homogeneous differential equation always possesses the trivial solution. We said if y is a solution, then a constant times y is a solution. And then we said if y1 and y2 are solutions, then you can multiply them both by constants and add them together and you get a solution. And then this next fact is one I will state without proof. We'll say an nth order homogeneous linear ODE possesses n linearly independent solutions And I'm going to underline that and put a big star by it. What that means is that this set of linearly independent solutions has no redundant functions. Here, none of these functions in our list, y sub 1 through y sub n, are redundant. And we're going to talk more about that when we talk about the Wronskian in the next video. But for right now, I just want you to learn this fact. We're not going to prove it. It says that an nth order homogeneous linear ODE possesses n linearly independent solutions, and we typically label those y sub 1 through y sub n. So if it's a fifth order equation, you'd expect five solutions, 5 linearly independent solutions. If it's second order, you'd expect 2 linearly independent solutions. If it's third order, you expect 3 linearly independent solutions, and so on. This set of functions is called a fundamental set of solutions. And I'm using that article A for a specific reason. So this set y sub 1 through y sub n is called a fundamental set of solutions, which we'll abbreviate FSS, of the homogeneous linear ODE that we were talking about. I'm using A here. I'm saying that this is a fundamental set of solutions because these are not unique. You could use a different linearly independent set of solutions. As long as you had n of them and they were linearly independent, that would work as well. Okay, now we know everything that we need to know to construct the general solution. This is what we were building up to. The general solution of the linear nth order homogeneous ordinary differential equation is this: y equals c1y1 plus c2y2 plus c sub 3 y sub 3, all the way down to c sub n times y sub n. So basically, you take all the functions in your linearly independent set of solutions, you multiply them by constants, you add them together, and that gives you the general solution. This is the family of solutions that contains all solutions. Once you've got this family of solutions that contains all solutions, if you also have initial conditions, you can use the initial conditions to find the values of c sub 1, c sub 2, c sub 3, all the way through c sub n. So for example, when we looked at this differential equation, and we said that y1 equals t squared as a solution and y2 equals t to the negative 1/3 as a solution. And if we multiply those by constants and add them together, that gives us a family of solutions. It turns out these are linearly independent, and we're going to talk about that more in the next video. Since these are 2 linearly independent solutions to this differential equation, they form a fundamental set of solutions. So when I multiply them by constants and I add them together, not only do I get a family of solutions, this is the family of solutions that contains them all. This is the general solution of the differential equation. And that's what we want. We want the solution, we want that family that contains all the solutions. This is a family. That's a nice family of solutions, but it doesn't contain all the solutions you're looking for if you're looking for all possible solutions to this equation. In order to have all possible solutions to this equation, I need these guys as well. But if I just had those, I'd be missing out on some of these. So in order to get all of them, I need to find all the members of this family and all the members of that family and add them together. And now I've got this family of solution that contains all the solutions to this differential equation. Let's look at another one. Let's say you've got y double prime equals y. I think we all know that y equals e to the x will work, because if I take the second derivative of e to the x, I get e to the x back. Because believe me, if I told you that e to the negative x also works, the derivative of e to the negative x is negative e to the negative x. And the second derivative of e to the negative x is a negative e to the negative x. The two negatives cancel and we just get e to the negative x back. So this is a solution and this is a solution, and it's a second order equation. And it turns out that these are linearly independent, which we'll talk about in the next video. So if I take these guys and I multiply them by constants and add them together, they form this is a general solution of the ordinary differential equation. And the two functions together, we would say, form a linearly independent set of functions or a fundamental set of solutions of the differential equation. So that's it for our discussion of general solutions of homogeneous nth order linear ODEs. The idea is this: if you're trying to find the general solution, what you want is n linearly independent solutions, one for every order of the derivative. So if it's a fifth order equation, you want 5 linearly independent solutions. If it's a third order equation, you want 3 linearly independent solutions. To find the general solution, you multiply them by constants and add them together, and that turns out to be the general solution. This idea of linear independence is really important. We're going to talk about that more in the next video.